Most college students have never known a world without the internet. There are any number of opinions about how the internet started, and like anything else, the issue is one that's been argued a number of times. Some would point out that it was packet switching that was proposed in some other part of the world, and that would be the beginning of the internet. Others will tell you that it was ARPA that marked the beginning of the internet. And a case could be made that, like so much other technology, the internet is the product of the space race. In 1957, the Soviet Union launched Sputnik, which was man's first attempt at space research or space exploration. It also caused the United States to aggressively begin a military campaign to compete with the Soviets. Soviets launched this satellite into space, and obviously those individuals responsible for the defense of our country considered it a possible threat, and so immediately went into action to compete with them. You have to remember the time. The late 1950s was a scary time for Americans because of the fear of nuclear attack. And ARPA was created as a result of this. It was the United States Research Agency for Space and Missile Research. You'll also see it written DARPA. It's really the same organization. It's been through a few name changes over the years. And of course, there's probably others that would say that Charles Babbage should be given credit, or even the Pony Express, or perhaps we can even say smoke signals from the local Indian tribe is beginnings of the internet. For the purposes of our discussion, we're going to take the ARPA point of view, Advanced Research Projects Agency. And in particular, we're going to suggest that it was really this gentleman, Dr. J.C.R. Licklider of MIT, who was the first head of the Information Processing Techniques Office at ARPA. Licklider was talking about a symbiosis of men and machines as early as 1958. In 1960, he wrote Man-Computer Symbiosis, which described some of his ideas, and once he became involved with ARPA, he was able to move forward with them. He had a big budget. It's interesting to find the number of times during a study of the history of the computer that the same names keep popping up. You remember this fella, Ivan Sutherland, the father of graphic design. Well, Mr. Sutherland replaced Mr. Licklider when Dr. Licklider went back to MIT. And Dr. Licklider influenced quite a number of other of these thinking outside the box innovators. You remember Doug Engelbart, the inventor of the computer mouse? He was also influenced by Dr. Licklider. Dr. Licklider was successful in convincing those that followed him at ARPA of the value of this network. In August of 1962, he wrote a series of memos, and in them he described this global network which people would access data and programs from anywhere. Does that sound familiar? Does that sound like the internet? He referred to it as an intergalactic network, or galactic network, depending upon the source. Ivan Sutherland followed him at ARPA, and then Bob Taylor after him, who was in charge of that same department from 1968 to 1969, when a lot of really exciting things happened. ARPA's goal was to connect mainframe computers. One of their goals was to connect mainframe computers at different universities so that they could share information even during network failures that could be caused by enemy attacks, nuclear explosion, or other catastrophes like the hurricanes that those folks in Alabama are so familiar with. Alabama Gulf Coast and Florida Gulf Coast and Texas Gulf Coast. According to one source, in 1965, another scientist from MIT developed packet switching. Packet switching is a way of breaking a large message into pieces called packets so that they can be sent from the source to the destination. At MIT, Leonard Kleinrock, this gentleman right here, published a paper on packet switching in 1961. And then Lawrence G. Roberts and Thomas Merrill actually made an interstate connection of computers swapping packets of data over a phone line. And this was before the late 1960s. And the result of all this was ARPANET. This was created in 1969. In the fall of 1969, the first node on this network was installed at UCLA. I found an image of a diagram somebody had written at that time, drawn at that time. What you're looking at there is the original internet. First node was created at UCLA. And by December of 1969, they had all four nodes: UCSB, Stanford Research Institute, which is now called SR International, and Utah. It was in 1969 that ARPANET delivered its first message. A message was sent from Dr. Kleinrock's lab, who he was at UCLA at the time, from Dr. Kleinrock's lab in UCLA to Stanford. And it said, log in. Another source I found said it was log win. I don't really know which was which. But what actually made it? LO. And then it crashed. But that was what you're looking at right there is the very first text message, email message ever sent on the internet. You know, and the internet's been growing ever since. Today, the term internet is generally accepted to mean international network of networks. And it's become so ingrained in society that it's hard to imagine life without it. It has allowed a flow of information that has increased human interaction through social networking, enabled incredible commercial successes, and even aided in revolutions. Revolutions that one day may result in freedom for many. It's so powerful that some governments do everything they can to limit their citizens' access to it, while other governments look for ways to tax it. It was during ARPANET development that many of the standards and protocols that we use today came about. Let's consider the challenges faced in a goal to connect devices across long distances. It really seems like a miracle that global communication can possibly work when one considers the vast number of manufacturers, providers, and people that are involved. Think for a moment. A person is in his or her den using any brand of computer, connected to a service through many other pieces of equipment, all made by any number of different companies, possibly passing through several different countries where people speak different languages. How in the world can this work? See my little graphic? Let's take a reverse look at this problem for a minute, because the 20th century was not the first time that a discussion of communication took place. We can't go further back than Genesis, can we? Perhaps you remember the story of the Tower of Babel. The people all spoke the same language. They decided that they were going to build a city with a tower that would reach to the heavens. They easily communicated with those who produced and delivered and assembled the materials because they all had the same language. They had no trouble at all in giving instructions to the craftsmen about how to build it because they all spoke the same language. In other words, they all followed the same standards of language and culture. But when God saw what they were doing, He said, they have begun to do this, and nothing they plan to do will be impossible for them. So He confused their language. Consider that story in the context of the internet today. Well, that was fun, but let's move on. It's the existence of standards that make communication like that of the internet work. So where do these standards come from? Well, for one, they can occur because some company has a monopoly for a long time. For example, until 1982, AT&T had a monopoly in the form of the Bell system. Up to that time, we did not even buy our own telephones. We leased the phones from an AT&T subsidiary, Western Electric. When the breakup took place, it was only a matter of weeks before people were able to buy their own phone at the local general store. How was that possible? It was possible because over the years, AT&T had developed standard configurations for all sorts of equipment, down to the small connector that plugged into the wall. In fact, there it is. That's called an RJ11. RJ11 is AT&T's own standard. And that is the connector that works with your telephone. Plug it into the wall. Another way that a standard evolves is by virtue of a product being so popular that its technology becomes the standard. Take Centronics, a major printer manufacturer, for example. Centronics was a major printer manufacturer in the 1970s when microcomputers first made the scene. And it was such a prominent company that the connector that they used to interface their equipment with computers became the IEEE 1284 standard. IEEE 1284. That is the Centronics parallel printer. That's a parallel printer connector. We don't use that anymore, do we? What is the connector we use now? USB? Yeah. But at the time, Centronics was such a dominant player that their technology became the standard in the industry today. And that's not the only example of that. For example, of where popularity of a product can make it a standard. How about the IBM PC? Now introduced in about 1980, it set the microcomputer world on its ear, and was so popular, in fact, that it became the standard for microcomputers up until today. Most of the computers that you'll find in your local business or even university computer lab is an IBM compatible computer, and that was because the IBM PC was so popular. How else can a standard develop? Another way that standards develop are through standard setting organizations, such as the IEEE that we talked about a minute ago. There is the International Organization of Standardization, usually abbreviated ISO, and it's made up of representatives from many other organizations. There's the Telecommunications Industry Association, TIA, the Electronics Industries Alliance, EIA, the ITU-T. All these are standard setting organizations dedicated to the task of creating those kind of standards that can be used for any number of different technologies. And they're made up of individuals from other companies, from other organizations, and they work together to make sure that a company that wants to develop products for the internet, for example, will build a product that will actually talk to something else. Now, we're not going to go into all the standards that evolved over the internet, but we'll touch on one. Let's take a look at this one. You see that little connector right there? That is an RJ45 connector. We've already mentioned the RJ11, right? That's the connector that hooks your telephone to the wall. Well, RJ45, also a Bell system standard, connects your computer to the network. The difference is the RJ11 has 2 pair of wires, 4 wires, whereas the RJ45 has 4 pair of wires or 8 wires. And so there is a standard for a connector. Well, take a look inside of this RJ45 connector. You see the 4 pair of wires that are in there. We have a connector that has 8 pins on it. That's RJ45. And a wire goes into each one of these pins. If you want to be able to transmit data over this thing, doesn't it stand to reason that there must be some sort of a standard for how those wires are going to be plugged into those pins? And there is. It's called the TIA/EIA 568B standard. Now, if you looked at and this, by the way, this connector connects with a particular type of medium called twisted pair cable. And that is the most common type of cable found on a local area network of computers. And the TIA/EIA 568B standard says that how these wires are to be connected. Now, if you were to look at a typical twisted pair cable, you would find that it has a white-orange wire and it has an orange wire. It has a white-blue wire and it has a blue wire. It has a white-green wire and it has a green wire. It has a white-brown and it has a brown. So I've got 1, 2, 3, 4, 5, 6, 7, 8 different wires with different colors. And really there's just orange, blue, green, and brown and in each pairs. And each of those pairs has one that's solid and the other one has a white stripe running down it. Well, all right, I've got this twisted pair cable. Now then, how do I pin it up? Because I could pin all these different wires in a number of different orders. And so if I want my computer to talk to the network, I'm going to build it according to I'm going to build that connector according to the TIA/EIA 568, which just simply says that the pins from 1, 2, 3, 4, 5, 6, 7, 8, from pin 1 to pin 8, it's white, orange, orange, white, green, blue, white, blue, green, white, brown, brown. That is 568B. There's a standard. Now, obviously, in a single lecture like this one, we cannot very well cover all the standards, even if it were possible to cover all the standards for all of the pieces that go into an international network of networks. But suffice it to say that the reason that the network works is because of the existence of such standards. When discussing communication among networks, usually one organizes the whole process into different layers, with each layer being responsible for some specific phase of the task. For example, one layer might define the physical components of the system to include the type of medium being used, such as copper or glass or air. You already talked about, for example, the RJ45 connector. There's a standard, and the TIA EIA 568B standard for plugging that category 5, that twisted pair wire into it. Those would be physical layer standards. Physical layer might also define the format of data as the ones and zeros as they're being shipped out. In other words, how the ones and zeros are being represented. Another layer might be responsible for the act of communicating between just two devices. For example, when you're sitting on your laptop and you're connected to the internet via wireless, you are immediately connected to the wireless access point closest to you, correct? Now, you may be trying to get to Amazon, or you may be trying to get to Netflix or somebody like that, but the next connection, the next hop, the next device in the line for you would be that wireless access point. And one of these layers would be responsible for the connection between your laptop and that wireless access point. What would it do? Well, it would do all kinds of things. For example, your computer might be some screaming high performance machine that can send data out in billions of ones and zeros in a second. But the wireless access point might not be quite that fast. Now, if your computer sent them all out there in the same speed that the computer could deal with, you'd probably be dropping a lot of bits or ones and zeros down on the floor because the access point couldn't process them fast enough. And so this layer that we're talking about, responsible for that connection, would be monitoring the speed and making sure that all those devices, those bit ones and zeros, were making it to the next hop. It would have an arrangement between your device and that wireless access point. And it also probably has some mechanism for your wireless access point acknowledging that it got them all. Another layer might be responsible for making sure that the message makes it from point A to point X, Y, or Z. For example, let's say you're on the internet and you're accessing Amazon and you are buying a book to put on your device, which may be the computer that you're on, or it could be an iPad or a Kindle or something like that. All right. Well, there's going to be one layer probably that's responsible for making sure that that book makes it from Amazon to your device in one piece. Remember that we're describing a packet switching environment. That is to say that that book is actually broken up in a whole bunch of little bitty packets that are being shipped out across the network. And all those little packets may be taking different routes to get to you. Understand that on the internet there's a whole lot of different pieces or hops along the way. And it isn't necessary that all the packets have to take the same route. But it is necessary that when they do get to the destination, they're put back together in the right order. And one of those layers would be responsible for that. They are called models. This is a model right here. This is the Open Systems Interconnection model, in fact, which is a model that's been taught in computer science courses at university for years. It has 7 layers, and each one of those layers does something different. Some of those layers are very well defined. Some of them aren't defined very well at all. But after 40 plus years of development, the model that has really taken control and communication, all internet communication actually follows this model, is the transmission control protocol / internet protocol model. And this model has 4 layers. Well, if we're going to talk about protocols, because we just said internet control protocol, I remember transmission control protocol and internet protocol, it might help us to define the term protocol. Protocol means rules used in communication. It makes no difference whether the task is a diplomatic communication or a network communication. Whatever, it is necessary that there be defined rules through which the entities involved, whether they be diplomats or computers, can communicate. The purpose is to ensure accurate information is passed between those entities. In the case of our network communications protocols, there are a bunch. Now, the 2 that make up the basis for the transmission control protocol and the IP internet protocol are TCP, which you would find at this layer right here, and IP. TCP stands for Transmission Control Protocol, and IP is Internet Protocol. And those 2 layers, transport layer and network layer, are the 2 layers that actually that those protocols apply to. In the case of TCP, its responsibility is make sure that that video makes it to you from Amazon in one piece. TCP couldn't care less how it gets to you. It's not interested in the routes that it takes or the addresses of all the machines on there. The only thing it's concerned about is making sure that that video makes it to you. TCP will arrange an appointment, let's say, between the sender and the receiver for the message that's being sent. And we already know it's broken into a lot of pieces, so therefore it's going to be responsible for making sure those pieces get put back together. The Internet Protocol, on the other hand, is a set of rules that, among other things, actually determines issues like the addresses of all the hosts along the route, along the global network. That's the IP address that we've heard so much about in years past. It's used in a TCP IP environment, and every device that's connected must have its own unique address. Now, that statement does reflect the essence of the Internet, but that carries with it some conditions that would need to be explained in a computer networking class, because it's not really true. But that's another story. The only entity that really has any semblance of global authority on the Internet is the Internet Corporation for Assigned Names and Numbers, ICANN. ICANN is responsible for allocating those Internet addresses, those IP addresses that we talked about. ICANN. ICANN. ICANN also doles out those domain names that you're more familiar with, such as www.amazon.com, which we're going to talk more about that in a little bit. IP also is the protocol responsible for determining the route that the packets will take to get to you. IP couldn't care less whether all those packets make it all the way out there to Z or not. The only thing IP cares about is that the route is figured out how it's going to get to Z, and that the packet made it to the next hop. It gets an acknowledgement. The next hop says, I got this packet. And at that point, IP couldn't care, it forgets about it, doesn't care anything else about it. So you see, when you're talking about these models, you're talking about different layers responsible for different things. ARPANET was eventually replaced by NSFNet, which finally ended up in what we know today as the Internet. The story of NSFNet is another story for another paper or another lecture. Here's an image of a TCP/IP network, and here you are right here, and here is Amazon, let's say, right there, and you are requesting information to come from Amazon, and that package could get to Amazon any number of different ways. And it would be TCP right here talking to TCP over here. So this is you, this is Amazon, and TCP on you is saying I want this movie, and TCP at Amazon said here it comes. And then whenever that movie gets over here, this TCP has got to make sure it gets put back together right. IP, on the other hand, here has got to figure out how to get to Amazon. And IP over here is going to have to figure out how to get your response. So there's a little diagram of a computer and how it works. Now let's talk about some of the applications that you would find on the internet. And going all the way back to ARPANET, the very first applications were these: email, file transfer protocol, that's abbreviated FTP, and Telnet, which was a utility for allowing you to log into a remote terminal. Email was probably the first. Well, you saw it. You saw them send that message login or LO. Would that be the very first text message ever sent on the internet? Yeah, it would, wouldn't it? Either the first text message or the first email message. File transfer protocol is a protocol that allows one device on a network to send a file of some sort to another device on the network. And it was developed, and neither one of these have anything to do with the World Wide Web, although the World Wide Web does utilize these protocols. Remember the name Mosaic because it used a number of internet protocols? Telnet, like I said, it's not used so much anymore because it's clear text. It's not encrypted at all, and so as a result, using Telnet is a little bit risky when you're dealing with confidential information. But in any case, these are three of the original applications of the internet: email, file transfer protocol, and Telnet. But now let's talk about the one that everybody knows about, the World Wide Web. World Wide Web and internet are not synonyms. World Wide Web is an application that utilizes the internet. It was invented by this fellow right here, Tim Berners-Lee, in 1989. He in fact coined the term World Wide Web. He wrote the first World Wide Web web server, called it HTTPD. By the way, that's Hypertext Transfer Protocol is what HTTP stands for. D stands for daemon, which is really just a memory resident application is what that means. So anyway, he wrote the first web server, and he also created the world's first web browser. He called his web browser World Wide Web. One great big word, no spaces. He wrote the first version of a scripting language used on the World Wide Web called Hypertext Markup Language, HTML. You've heard about it. This is a document formatting language that has the capability for hypertext links that became this has become the primary publishing format for the web. His initial specification for Uniform Resource Locator and Hypertext Transfer Protocol and HTML have all been refined and are still used today. The World Wide Web is to a great extent based on its own protocol called Hypertext Transfer Protocol. There you go. And it enables the transfer of documents and graphics and audio and video files. And there's any number of different scripting languages like these you see over here. We mentioned HTML, although I don't have it listed here. Here it is down here at the bottom, HTML. Java, PHP, by the way, PHP originally stood for personal home page, but it's a very, very popular web scripting language. It's usually used to script server type applications. Others are Visual Basic, Visual C, Java, JavaScript, C++. Those are all web programming languages. But the original, and most of these things work with HTML for that, frankly. They work together. The Uniform Resource Locator, that is how you access a remote web page. You input the URL into that address slot on your web browser. It shows you the protocol being used, HTTP. It identifies the domain that you're accessing, in this case en.example.org. Wiki is a server on that domain, and the main page, main_page.htm, that HTML right there tells you that that's a hypertext markup language file. As far as the web servers are concerned, there are two primary ones, Apache. There are any number of web servers, but the two dominant ones are Apache, which is a Unix or Linux-based web server, and IIS, which stands for Internet Information Services, which is a Microsoft product. Those are the two dominant web servers in use today. Web browsers, well, there's Mr. Berners-Lee's World Wide Web right there. And then came Mosaic. Mosaic was developed by the National Center for Supercomputing Applications at the University of Illinois in Urbana-Champaign beginning in 1992. Supposedly it got its name because it supported multiple internet protocols, not just HTTP, but FTP and the others. Mosaic was soon followed by Netscape, and then shortly thereafter Microsoft got into the game with Internet Explorer. Netscape kind of got brushed aside by Microsoft, but it was picked up and is the basis for Firefox, another very popular web browser. Opera is a web browser not so well known here. Safari is your Apple version of a web browser, and Google Chrome is also a very popular web browser found today. And they all do the same thing. And which one is better than the other is personal opinion. I use Google Chrome usually, but I happen to like the others as well. The URL is simply the address you put into the web browser. Now then, speaking of accessing data on the internet, in the World Wide Web, you can access anything you want to access on the web if you know its address. For example, if you put in 176.32.98.166, that will take you to Amazon, www.amazon.com. If you put in 50.112.92.119, that'll take you to Netflix. Now then, imagine trying to remember the IP addresses of your 10 favorite websites using those numbers. Would that be a bear or what? Human beings don't deal with numbers that well. One of the reasons we use decimal instead of binary. A decimal number, you can use 4 digits to represent up to 9,999. 4 digits in binary represents 15. So humans don't deal with those long numbers that way. So they came up with a naming scheme to make it easier on you. And it's called the domain name system. Domain in this case means a range of legal values. For example, a domain of states would have 50 values in it. A domain of months would have 12 values in it. See? And in the case of the domain name system, this is a system that has a range of legal values that are assigned by ICANN and that allow human beings to now input a name that they can easily represent to get to their favorite website. How good is that? Well, let's see. If you wanted to go to Ford, what would you enter? What you want to bet? www.ford.com would take you there. Your most popular places, you can pretty much easily figure out where they are simply by using something logical. If I want to go to Hewlett Packard for printers, I bet you I can go to www.hp.com. So the domain name system is significantly easier to use than those IP addresses, and that's why we use it. Over here on the right are a number of high-level domain names. This is the highest level right here. .com stands for company, .org, organization, .edu, education, MIL, military address, .gov, government address. You need to check on your health insurance. You might be able to go to www. What do you suppose it's called? Affordable Care Act, ACA? I don't know. I know if you go to www.irs, you'll get a website that you can expect. And then .net is a website that or a domain name that usually represents some sort of a provider, like bellsouth.net or somebody like that, or AT&T.net. So these are the highest level. And when you look at the names here, you see that that is Amazon's domain name. That's the one that they bought. .com indicates that it's a company. www.umobile.edu. Edu tells you it's an education institution, and that one happens to be the University of Mobile. And so you see how the domain name system works. Very, very handy and helpful. Finally, is anyone in charge of the internet? The answer to that is many people are in charge of the internet. At least they're in charge of their own piece of this vast network. The system administrator for each autonomous network that is connected to the internet has as much control over what they will allow on the web as they need when users access it from their network. So an administrator has the ability to filter internet traffic based upon the organization's policies. Now, if the question is, does anyone have control of the global internet? The answer is no. Then one might ask how governments restrict access if no one is in charge. They do so by means of laws that govern those businesses that provide internet services. For example, if an internet service provider, ISP, wants to keep its license to do business, then obviously it must comply with any law established by the government, which would include filtering traffic. Of course, that's in a country run by laws. In conclusion, the difficulty in communicating along a vast network of devices on the internet would seem insurmountable when one considers the sheer number of different entities involved. The variety of hardware necessary is daunting, as is the variety of people, services, and even countries involved. Yet, as we have seen, it is all possible because of the existence of well-defined standards and protocols that have been developed for the task. In addition to that, there have been some excellent applications such as email and the web created to enable us to access people and services all over the world. The result has been a fantastic increase in the power of men and women over their own lives, to be able to compete in business and politics, and to truly change the world. Remember, though, what happened when men demonstrated that kind of power back in Babylon many years ago. That concludes this lecture.